This video is part 2 of a 3-part thermodynamics video series, and what we want to talk about in this video is Gibbs energy or free energy. After today's video, hopefully you'll understand what Gibbs energy is, know its symbols and units. You'll know how to calculate it. You'll know how to interpret it when you see a free energy value. You know how to evaluate spontaneity of a reaction based on Gibbs free energy. And when a spontaneity is temperature dependent, find where what we call the crossover temperature, which is the temperature above or below which things become spontaneous. So let's go back to a reaction we talked about in the last video, where you're basically just burning methane. It's common natural gas we use to heat our water or to cook on the stove. And we know that as things happen, the gas burns, creates heat. It's an exothermic reaction. And we know that from the last video that this is spontaneous, that basically the entropy that's created in the environment makes up for the entropy lost in the system. And basically in thermodynamics, you're really wanting to know two things that have practical applications. So one of the things you want to know is whether the reaction is spontaneous or not. And the other thing you would like to know is how much energy you can use from a reaction based on the chemical potential energy that's stored in the breaking bond forming events. In the past we talked about utilizing the heat, but I don't want you to misunderstand that usable energy or free energy can be used in different ways. So in the case of methane, in the last year, we've actually increased the amount of methane we've used to create electricity. So we're lowering our dependence on coal, and we're increasing the amount of electricity we generate with natural gas. But of the chemical potential energy that's stored in every mole of methane, the question is, how much of that energy can I use to actually create electricity? Or maybe we use it for transportation. I know here in Denver we actually drive some of our shuttle buses up and down the 16th Street Mall on methane gas. And usually if you have a vehicle that's powered by compressed natural gas or methane, you'll see this little symbol on the side of the vehicle, the CNG sticker. And this is a little side note that's a little unrelated to energy, but just of interest in regards to methane. It's also a chemical feedstock that's used for making ammonia, fertilizer, methanol, and hydrogen. But once again, we're back to that fundamental question of the chemical energy that's available in methane. How much electricity or transportation movement can we actually generate? What's actually usable? And that's where Gibbs free energy comes in, or Gibbs energy or free energy as it's referred to. Because the Gibbs standard energy or reaction is a measure of the energy that's available from the chemical potential energy that can be released in a reaction or that can be used in these ways. The units for it are commonly in kilojoules per mole, some sort of energy per mole. Usually when you're looking at a table, you'll see Gibbs free energy measured, but it tends to be assumed that it's at a given temperature and pressure. And usually that temperature is 298 K. In general, you can start with your heater reaction, but you're going to lose a little bit of the potential from the heater reaction because you have to pay an entropy tax. And entropy is what we talked about in the last section. Gibbs free energy can also be used directly to measure spontaneity. As we've talked about in the last video, you can do this from the entropy standpoint and say, well, if the entropy of the universe is increasing according to the second law of thermodynamics, and that also would give rise to a spontaneous reaction. But Gibbs free energy is also a direct measure that allows you to determine whether a reaction is spontaneous. And just a little bit of the history there. The free energy is assigned with the unit G after Josiah Gibbs, who discovered it. And just, I always try to describe like pressure is really the true effects of force. If you really want to know how much of damage or effects that force has, you would actually want to measure pressure. In the same way, of all the energies you might measure, Gibbs energy or free energy is the proper measure that will actually tell you usable energy that comes from a chemical reaction. So here we go. Here's the formula, the Gibbs equation. I've got it rearranged from the way it's traditionally written, just so you can understand it a little bit. And that is heat reaction, which we've studied in General Chemistry 1, basically which accounts for the energy required for bond breaking events and the energy released in bond forming events. That net energy actually is available for use, but you have the Gibbs energy, which is really what's available to use for, running a battery, running an engine, doing chemical reactions. But you always have to pay, in addition, the entropy tax, which is what's dispersed to the universe. So as we've learned in the last video, that's actually temperature dependent. What is the Gibbs energy telling me? So in terms of spontaneity, here's how you interpret a Gibbs measurement. If the Gibbs energy is less than 0, you have a negative sign on it, then that is automatically a spontaneous process. If the Gibbs energy is greater than 0, then that indicates that it's a non-spontaneous process. And if the Gibbs energy is exactly equal to 0, then at that point you can assume that the reaction has ran until it's reached equilibrium. So I can no longer harvest energy from that. Now, as far as the useful or free energy, anytime the delta G is less than 0, that is actually a measure of the useful energy. And remember, according to the first law of thermodynamics, that whatever energy is lost, the Gibbs free energy is negative, that's given off by the reaction, that is the exact same amount of energy that can be utilized by another reaction. It's a sign change, but remember what the convention means. If it's negative, it means it's leaving the system, or in this case, the chemicals where the reaction is taking place, and it's being picked up by the surroundings. So how do you calculate the delta G? The Gibbs equation basically shows you that you can take the enthalpy of the reaction, the heat of reaction, you subtract it by the temperature, and once again, this is the temperature at which the reaction is taking place. In essence, it's the temperature of the surroundings of the reaction. And then you multiply that by the entropy of the reaction, which we've learned in the last section you can calculate from entropy tables, as you can calculate the heat of reaction from heat of formation tables, all contained in a thermodynamic table. Another way to do this is to calculate it directly from a thermodynamic table using the Gibbs energy of formation, which is analogous to heat of formation. This is the Gibbs energy of formation. It's the free energy required to make the reactants from their standard state. In analogous manner, your elements and your diatomics are considered to have a Gibbs energy of 0. But once again, pay attention that you do the product minus the reactants. So whatever the reactants are, you change the sign on those. So let's do an example here. This is where potassium chlorate is converted to potassium perchlorate with heat. This is a chemical reaction where potassium chlorate is used in explosives and fireworks. It's just more stable than the potassium chlorate, so a lot of times that's converted over. And this is a disproportionation reaction in which the chlorine is both oxidized and reduced in the same reaction. But once again, you go back to your thermodynamic table. Something I like to do is just basically build the table. Use this reaction like columns. Your reactants and your products, just build columns underneath there. And then what I like to do is I figure out the heat of reaction, the Gibbs free energy, and the delta S by just basically filling in the columns. So remember that we do this in terms of products minus reactants. So whatever I put in the reactant side, I change the sign. And the other thing is I want you to notice that enthalpy and the free energy are both in kilojoules per mole, but when you look at the entropy, it's actually in joules per mole. That's 1,000 times different in size. So what you want to do is make a conversion, either make these kilojoules into joules or joules into kilojoules. And I tend to always just move the decimal over 3 times on my entropy. I'm going to go over here and start filling in the blanks. And once again, this is a reactant, so I need to change the sign on it. The other thing is you need to multiply by the coefficient in front. because you have 4 moles in this balanced chemical equation. Here you have 3 moles of the potassium perchlorate, so you multiply by 3, keep the sign the same, and then 1 mole of potassium chloride. Then you can just sum across. Once you have it set up in this way, this is why I like to do it like a table. Then I can just take these multiplied together and add them to these and add them across and sum all 3 of these together and get my answer. So the heat of reaction is minus 144 kilojoules. It's exothermic. It's losing energy. I go in and use the free energy, do the same thing, and notice that it's less, and we would expect it to be less because remember you have to give up some free energy tax. But in terms of spontaneity, this is favorable because you're losing energy, and we know that that tends to, that's favorable to being spontaneous. But last but not least, we have entropy, and we can look at this beforehand and kind of make a prediction. These are both solid state, and I haven't really gained that many more pieces. I got 4 solid pieces here, and I got 4 solid pieces here, so this went up in complexity, this went down in complexity, so this probably should be very close to a wash or very low change in entropy just based on what we learned in the last video about quantitatively analyzing entropy. So go through, do the calculations, and sure enough it's a very low, actually a loss of entropy of 0.03681 kilojoules per K, which is temperature. And I just want to remind you again that the units here, I changed the decimal over 3 times for each one of these calculations, and that just simplifies it so these can all be compared together. So just by looking at the free energy, because of the fact that it's negative, we know that it's a spontaneous reaction. Okay, you don't have to look at anything else when you have that. But for comparison's sake, if you want to do it the other way, right, you can take the enthalpy of reaction here, which is minus 144. You minus the temperature. Now these standard tables are all set up at 298 Kelvin. So that's going to be the temperature. And then you multiply that by the entropy. And when you do this calculation, you came out with the same answer to 3 significant figures is negative 0.133 kilojoules. And once again, this reaction is spontaneous because you see a negative sign on the delta G. If it came out 0, it would not be spontaneous. It would be at equilibrium. If it had come out positive, you would know that it's non-spontaneous. So this reaction has 144 kilojoules of chemical potential energy. That's what that tells me. The bond-breaking, bond-forming events release 144 kilojoules. But that is not all usable because you have to pay the entropy tax. That's this entropy that's actually lost times the temperature. That's 11 kilojoules. Once you subtract that out, though, then you get the free energy, and that is what's actually usable. And if you wanted, you could run this reaction to power a battery, or you could use it to heat a space or maybe lift a weight. Whatever you want to do with it, the free energy is actually the proper measurement to use to figure out how much usable energy is there after you pay the entropy tax. So now comes the next question, and this is where Gibbs' equation is helpful because most of these tables are set up for 298 K, but as you know, a lot of reactions are not going to be ran at 298 K. And according to Gibbs' equation, as you change the temperature, it's going to change that free energy outcome. So it's going to change the spontaneity. So just to prove the point, we're going to look at this reaction and kind of change the temperature a little bit. So the first reaction we did, we basically ran it at 298 K. You do the calculations, you see that it's actually spontaneous. But just for grins, let's raise the temperature a lot. Let's raise it up to 5,000 K and see if this is still true. And so you now do the calculation, and you see that the free energy that comes out of this calculation is actually positive, which means it's non-spontaneous. So what this means is that at some temperatures this reaction runs spontaneously, but then at another temperature, at higher temperatures, it apparently changes spontaneity. So this gives rise to the concept of what we call crossover temperature. There's obviously some temperature at which it changes from a spontaneous to a non-spontaneous reaction. So where is the crossover temperature? How do you find that? So we're basing it on Gibbs equation. And now what I've done here is I've put up a graph where we're basically going to figure out the Gibbs energy at different temperatures. We're going to start it, and remember this is in Kelvin, so the lowest you could go. This is theoretically 0, which is not really obtainable. But if there was such a thing and you did the calculation, at that point you literally would harvest all of the bond breaking, bond forming from it. And then as you start to raise the temperature, you can see that the Gibbs energy falls off. So now we're approaching 0. But at this point, I want to just point something out. Anytime that the free energy is less than 0, that's usable energy. So anytime that you have a delta G that is less than 0, you literally have, at these temperatures down here, you have free energy available and the reaction is spontaneous. But then, when you get to around 4,000 degrees K, the free energy is 0. So that's what we call the crossover point. We go from where free energy is available, or where it's spontaneous, to where it's at equilibrium and there is no free energy available. And then as you keep raising the temperature above 4,000 K, now all of a sudden the delta G is positive, which means there's no free energy available, and it is no longer spontaneous. If you wanted to run the reaction at these temperatures, you would have to pump in energy from the outside. So let's figure out where that crossover temperature is. The idea is it happens at equilibrium, and we know that that actually occurs when the free energy equals 0. So we're going to plug in 0 for free energy, and what we want to do is solve for T, the temperature at which that occurs. Do a little algebraic manipulation, bring the T delta S to the other side, and then divide out by the entropy. So this is the equation you want to use whenever you want to find the crossover temperature. Basically just divide your delta H by delta S. So now if I take my enthalpy, which is minus 144, and I divide it by the entropy, which is minus 0.03681 kilojoules per K. Now I'm dividing by a fraction. I'd invert and multiply. My kilojoules would cancel, and as a result I'd get 3,912 K. And that is the crossover temperature, and that is the equation to find the crossover temperature. Now, is there always a crossover temperature? You can imagine that according to that equation, there's not always going to be a crossover temperature. So we're going to figure this out based on using the Gibbs equation. So to understand this, let's just think about this. What scenarios are favorable for spontaneity? In terms of the enthalpy and the entropy, well, we know that when the enthalpy, the heat of reaction, is actually exothermic, or the sign would actually be negative, so I'm putting in a negative here, right? We know that that is favorable for being a spontaneous reaction. And we also know that when the entropy is increasing, which means that the sign on that would be positive, then in that condition, it would be spontaneous at all temperatures. So anytime you have a reaction where you have a heat of reaction that's negative and an entropy that's positive, no matter what the temperature is, it's going to be spontaneous. Because in that case, no matter what numbers you plug in here, if they have these signs of positive and negative here, the positive times the negative would make this whole piece of the equation negative, or a minus plus a minus in essence, would give you a free energy that's always negative. So it's always spontaneous. Well, what scenarios don't lead to spontaneity? Well, that's when your heat of reaction is positive. It's an endothermic reaction. And the other scenario is when the entropy of the reaction is actually decreasing, which would make it negative. And when you see signs of positive on your heat of reaction and a negative on your entropy, in that condition, you're never spontaneous, because the delta G would always be positive. So let's take scenarios where it's mixed, where you can actually have a situation where it's endothermic, which is not favorable to spontaneity, but it is increasing entropy, And so you can imagine that if the temperature is low enough, then this particular factor is not influential in determining whether it's spontaneous or not, until the temperature gets large enough so that this factor overall increases and overwhelms the fact that the enthalpy is not favorable to spontaneity. At high temperatures, the negative factor would override the positive factor. And then the other scenario is, now I have a heated reaction that's favorable to spontaneity. It's exothermic. But then I have a entropy that's decreasing, which is not favorable. And so if this temperature is low, then this factor altogether has very little influence, and the negative sign comes from the enthalpy. But whenever the temperature gets high, then all of a sudden the entropy starts to override. And so that would be spontaneous at low temperatures. You need to study this chart and put some numbers in there until you understand that, so that you can look at the signs on the enthalpy and the entropy and decide whether there's a crossover temperature and whether the spontaneity occurs at high temperatures above the crossover temperature, at low temperatures below the crossover temperature. Now what I'd like for you to do is just kind of practice all these things we've learned here. I'm going to do a reaction where you take copper 2 oxide and you decompose it into actual copper, solid copper, and oxygen's given off. And take your thermodynamic table, so you'll have to take one out of your book or one that I've handed you in class, and figure out your heat of reaction, your free energy of reaction, and your entropy of reaction. And then answer the following questions. Is the reaction spontaneous at 298 K based on the delta G? Can you qualitatively look at the reaction and tell me, hey, this should be, in terms of entropy, be increasing entropy or decreasing entropy? Is the reaction exothermic or endothermic based on, of course, your heat of reaction? Is there a crossover temperature based on the chart we just looked at? And if so, can you solve for it in Kelvin? And then if you understand that, do you know whether it's going to be spontaneous above or below the crossover temperature? So at this point, stop the video, solve these problems. When you're done, you can restart the video and check your answers. So let's see how you did. So let's start off by getting your enthalpy, your free energy, and your entropy calculations. And like I said, I usually just build this into a table, use each of the reactants and products as a column. I find my table from the book or what I've been handed to you in class. Take your thermodynamics table, use your heat of formation. Okay, and remember that on the table, if you'll look, there's a reference point. It's usually at 298 K. And also, I'm going to take my entropy in particular and convert it to kilojoules. I want them all in the same units. And I remind you once again, and I'm using the free energy calculation, that it's products minus reactants, so you got to change the sign on all your reactants, which in this case is copper 2 oxide. So I go to the reactants or products side first, and fundamental elements are zero heat of reaction. The same thing with free energy or Gibbs energy is zero. The entropy for making copper solid, remember the reference point there is we're at 298 K. It would be at 0 if you were at 0 K, which is kind of a theoretical point. So now I have oxygen, which once again is a diatomic fundamental element. That's 0 on the enthalpy and 0 on the free energy or Gibbs energy. Remember to multiply by the coefficient, which is 1/2. Now we're going to the copper 2 oxide. It has a measurement of heat of formation of minus 157.3 kilojoules per mole. Make sure you change the sign. There's no coefficient in here. Do the Gibbs energy. And finally do the entropy, and don't forget to move the decimal over 3 times so everything's expressed in kilojoules. Now you can just sum across with your calculator. You see that the heat of reaction is 157.3 kilojoules. The free energy is 129.7 kilojoules. And this should be a check that makes sense, that whatever my heat of reaction is, you'll lose a little bit in terms of paying the entropy tax. So, is the reaction spontaneous at 298 K based on the delta G reaction? Well, the delta G reaction is positive, so the answer to that is no, it is not spontaneous. Okay, if it had been negative, it would have been spontaneous. Can you qualitatively look at the reaction and predict the sign of entropy? So, you know, the sign is that it's gaining entropy, and let's see if that makes sense. I'm starting off with one solid reactant, and I'm making a solid product, but I'm also making a half mole of gaseous product, and we know that this is definitely a higher entropy than the solid state. So it makes sense that you're increasing entropy a little bit. Okay, and this is confirmed by the positive number. Question 3, is the reaction exothermic or endothermic? Well, you look at your free energy or your heat of reaction, and that's positive, so it's actually endothermic. Okay, and that is not favorable to spontaneity, by the way. So now, is there a crossover temperature for this reaction, and what is it in K? Well, let's evaluate if there's a crossover temperature. First off, I have a heat of reaction that's not favorable, but I do have an entropy that is favorable, so I know that if I take my term entropy times temperature, it will increase this. So yeah, there must be a crossover temperature. Okay. And how do you find that? Well, you take your enthalpy divided by your entropy. Remember, your kilojoules cancel, you're left with Kelvin. And this occurs at 1,710 K. All right. Next question. So if we understand there's a crossover temperature at about 1,700 K, is it spontaneous below the crossover temperature or above the crossover temperature? So let's walk through this again. Remember, as things stand right from the beginning, at 298, we know that it's non-spontaneous. So that would kind of answer the question already, but we can walk through this and think it out and go, okay, well, my heat of reaction is not favorable to spontaneity. It's endothermic. But my entropy is, so I have to have temperature multiplied by this factor and increase the temperature so that this becomes the overriding factor, right? Because you only multiply temperature times entropy. And as this factor gets large enough, it will start to override this factor. Make the overall equation negative, which is favorable to spontaneity for free energy. And then last but not least, this isn't one of the questions, but you can always do this. This is good to double check your work. You figured out the free energy. You did it directly off the table. But we know, according to Gibbs' equation, that if you'll take your delta H minus temperature times your entropy, you should still get the same Gibbs free energy. So if I plug in my numbers and double check, I come out spot on to the significant figures I've been given of 129.7 kilojoules. So I hope this has helped you understand Gibbs free energy, to know its symbols, to know its units, usually in some sort of joules or kilojoules per mole. Know how to calculate it using both the Gibbs equation and also to use products minus reactants using the Gibbs energy formation. Know how to interpret it. If it's a negative sign on it, we know that it's spontaneous. If it's positive, it's non-spontaneous. If it's zero, it's at equilibrium. Then know how to interpret the spontaneity based on the signs of H and S. In other words, know when there's crossover. And when it is temperature dependent, can you find where the crossover temperature is? Enthalpy divided by entropy. So I hope this has helped you understand Gibbs free energy and to understand thermodynamics better.